In this video, we will be describing some of the different distribution functions related to quantum mechanics. In particular, the radial distribution function and the probability distribution function. It is these functions that give the orbitals their various shapes. As was mentioned in a previous video, if we take Schrödinger's wave equation, which is represented by a capital psi, this symbol here, and we square it, we obtain the probability density function. The probability density function is essentially the probability of finding an electron at a particular point in space as a function of the distance from the nucleus. So what we mean by that is, what is the likelihood of finding an electron at a given distance from the nucleus? The wave function describes the general shape of a wave. An example of something that utilizes a wave function is a string that is being held tightly between two set locations. When it is plucked, it will move back and forth, forming wave-like shapes, where you have the string going up and down, going from peak to crest, but not traveling down the line. In between the various peaks and crests, you'll find nodes. These are locations along the string where it does not move. So a node in the function is where the probability is equal to 0. So if we take our wave function here, and we have particular locations where the probability is 0, so our wave function is essentially describing the probability of finding the electron, where we have a high value is where we would have a high likelihood of finding the electron. These locations here, the nodes, sit on the 0 of the axes, the 0 of the vertical axes. And because they are 0, if we square 0, we get back 0. So where these nodes are located, the probability of finding an electron at that particular distance is equal to 0. In addition to the probability density function, we also have the radial distribution function, which represents the total probability at a particular distance from the nucleus. It takes into account both the probability density, which is the probability of finding it at a particular radius from the nucleus, as well as the volume of space that is taken up by that particular radius as we map it out into three-dimensional space. The maximum value is called the most probable radius, and is what we will use when we are trying to describe the size of an orbital. The probability density function, which again is the square of the Schrödinger wave equation, represents the total probability of finding an electron at a particular point in space. For the 1s orbital, which would be where our n value, our principal quantum number, is equal to 1, and our L value, which tells us the type of orbital, would be equal to 0. We can graph the probability of finding an electron as a function of the radius. For the 1s orbital, it has this particular shape, where we have a high probability of finding the electron at a point that is very close to the center. Now, it should be mentioned that this is the probability if we look along a straight line. If we take that line and map it out in three-dimensional space, we get a radial distribution function. So the radial distribution function represents the total probability of finding an electron within a thin spherical shell at a distance r from the nucleus. We could think about this graphically. We have our original probability distribution function, which again is our psi squared from our previous slide, which looks like this as we map it out against the radius. So this is the probability along a straight line. If we're interested in determining the probability of finding an electron at a particular distance from the nucleus, what we need to do is take into account not just the probability along a line, but map that line three-dimensionally. Typically, when we're talking about probabilities, we need to talk about what is the probability of finding an electron between two different locations? So we could think about it in terms of the radius as being between two values that are very close together. If we're looking along the radius, then here are our 2 points. We can then map out that radius three-dimensionally, and what we end up with is a sphere that is hollow. You can think about it sort of like a candy coating, a thin shell around a void of space. So what we're interested in is what is the probability of finding an electron at a particular distance from the nucleus. And because we're mapping it out three-dimensionally, that would be a thin spherical shell. So from our probability distribution function, which is this one here, the probability at a particular point decreases with increasing distance from the nucleus. But the volume that we're mapping out here increases as the shell increases. So as we go further and further out, the spheres become bigger and bigger, and so they will take up a larger area. The total radial probability is a combination of these two functions. So the radial distribution is going down in value, but we're multiplying that by the volume that we're looking at. So the volume will be increasing as we get away from the nucleus, whereas the probability will be decreasing. So if we multiply these two together to get our total radial probability, there will be a point at which the combination of the two gives us a maximum value, right? Our probability distribution function is going down, but our volume is going up. So when we multiply the two together, there's a maximal value for the total probability of finding an electron at a particular distance. That maximum value is what we call our most probable distance. When we're looking at orbital diagrams, what we will be showing is a graph of the orbital, and the outer limit of that graph is going to be the maximal value, again called the most probable distance. From the value for a hydrogen atom, the net result is a plot that indicates the most probable distance of finding the electron in the 1s orbital, and for hydrogen, that value is 52.9 picometers. When we go to the larger s orbitals, the 2s and 3s, what we see is that there is a node in the probability density function. So the top two graphs here are the probability density functions, and the bottom graphs are the total radial probability functions. For the 2s orbital, there is a point in space that there is a zero probability of finding the electron. So the electron has a region of high probability, followed by a region where there is zero probability, and after which there is again a region of high probability. Looking at the graph that pans out, you have this first region with a high probability, a node where there is zero probability of finding the electron, and then another region where there is a high probability. When we combine this with our volume shells that was described in the previous slide, we get our total radial probabilities. Taking into account how the volume of space increases as you get away from the nucleus, what we find is that there is a non-zero probability of finding the electron at the nucleus, followed by a location in space or a particular distance from the nucleus where you will not find the electron, followed by this region where there is a high probability. The presence of a non-zero probability here will become important later in the semester. The 3s orbital also has that spherical shape because it is an s orbital. It has, again, a non-zero probability of finding the electron close to the nucleus. Then there are now two nodes where there is a zero probability of finding the electron. So again, this top graph is the probability density function. There are two nodes, one here and one there. Between the nodes and after the nodes, there are regions that have non-zero probability. If we take the probability density function and multiply it by those volume shells that we were talking about when we map our volume area three-dimensionally to get our total radial probability, what we find is that there is a non-zero probability of finding the electron at some different locations away from the nucleus, with the largest probability being much further away from the nucleus than what we saw in the 2s. And for the 2s, this maximal probability is further away than what we would have seen for the 1s. Again, when we are looking at the orbital diagrams that you'll be seeing in subsequent videos, what we are looking at is a representation of the probability of finding an electron in that region of space, with the outer part of the graph being these maximal values